Hi everybody, I hope this video finds you well. In today's video, we're going to be working through practice number 10, which focuses on questions related to one sample proportion procedures and two sample proportion procedures. As usual, I would strongly recommend making sure that you finished all the videos for these sections for one sample proportion procedures and two sample proportion procedures, and you've tried these two questions yourself before watching this video. If you've already done that, if you've already watched the associated lecture videos and tried these questions yourself, well, then let's get started actually working through these examples. So for question 1, it tells us that in 2010, it was reported that 68% of all U.S. households owned a pet. You want to study if this percentage has increased. So to study this, you divide the country into 4 major regions: East Coast, Midwest, South, and West Coast, and you randomly sample 60 households from each region. This means that we ultimately randomly sample 240 households and find that 168 of them owned a pet. So we've got a couple things to do here before we start going through this and dissecting all the crucial information. Let's talk about what types of questions we want to be able to do here. So in part A, we want to be able to carry out at alpha equals 0.05. Remember, that's our significance level. A hypothesis test to test the claim that the percentage of U.S. households that own a pet has increased since 2010. We're going to check all the conditions and state our conclusion in the context of the problem. That's always the standard thing we do with hypothesis tests. Then in part B, we're going to build a 95% confidence interval to estimate the current percentage of U.S. households that own a pet. And again, we'll check the conditions and make sure to interpret it. And then at the end here for C, we're just going to do a little bit of sort of review way back to the sort of beginning of our class about sampling techniques. We're just going to remind ourselves what type of sampling was used here to actually construct that sample. All right, so with that in mind, let's go ahead and start thinking about how we're going to set up that part A here. So for part A, we want to carry out this hypothesis test. So that means we need to determine what type of hypothesis test we're going to need to do. At this point in our course, we have 5 different hypothesis tests that we've talked about. We have the one sample mean, the two sample mean, matched pairs, and we have one sample proportion and two sample proportion. Now, of course, we know that this practice focuses on the proportion procedures, but what in this problem sort of identifies that to us? Well, the first thing is we see this mention of percentage in here, right? We see 68% is listed as one of the values. We also notice that the claim is you want to study if the percentage has increased. So that word percentage shows up several times. As soon as you start seeing mentions of percentage, you know you're working with something that is a proportion procedure. So now we need to decide, is this a one sample proportion or two sample proportion? Well, if we look at this, we know that we randomly sampled 240 households. So we built one sample. So this is going to be a one sample proportion hypothesis test. So one sample proportion hypothesis test. Remember, in a little bit more detail, what that really means is that we have one sample of binomial data, which it is, right? Every time we talk to one of these households, they either own a pet or they don't, right? That's a binomial categorical variable versus a known / assumed percentage. And what is going to be that known or assumed percentage? Well, we know that that's going to be that 68% that was true back in 2010. All right, so let's start actually going through the 5 steps of the hypothesis test. So for step 1, we have the hypotheses. So that means we have to set up our null and our alternate. So because we're doing a proportion test, our sort of notation is going to be P equals, and then P and that same value and some inequality there. So as is usual with these one sample procedures, we've sort of got 2 things to do here. We have to figure out what value should go there, and we have to figure out what inequality should go there. So let's start with this null hypothesis. Remember, the null hypothesis should be that known or assumed percentage. And as we said, that should be that 68% that was true back in 2010. We can write it as 68%, but when we actually start to do our computations, we'll need it as a decimal. So we might as well write it as a decimal now. So we'll put 0.68 there and 0.68 there. Okay, now we need to focus on our alternate and figure out what is our claim. So remember, this is what we want to study. So it says right here, you want to study if this percentage has increased. So since we're trying to study if it has increased, we'll put P greater than 0.68. So our baseline assumption is that the percentage of U.S. households that own a pet is still 68%, but our claim is that it is greater than or has increased from 68%. In the past, we would have called this a one-sided test, but remember with proportion tests, we want to be a little bit more specific and we want to say actually which side is it going to be. Since we're using greater than, that means this is going to be a right-sided or right-tailed test. So right-tailed test. If it had been less than, if we had p less than 0.68, it would be a left-tailed test. And if it was not equal to, then we'd still use that same language of a two-tailed or two-sided test. All right, now that we have those hypotheses, let's go ahead and check our conditions. So for the first condition, this is one we've checked many, many times. It's the first condition of every hypothesis test we've studied thus far. The data needs to be random and representative. Well, it does say right here that we did this process where we selected 60 households from each region, which meant we ultimately randomly sampled 240 households. So that does mean that it was done randomly. So this was stated. So we're all good there. The second thing we need to make sure is that our sample size is less than 5% of our population size. Now, of course, we always know the sample size. In this case, it's the 240 households. Sometimes we have information about the population size, sometimes we do not. In this case, there is no mention of the number of households in the U.S. overall, but of course we know that that's going to be a massive number. So all we need to do is just simply say lots of U.S. households. So we're all good there. We'll put a check mark. Now, notice that when we state this, we're stating the population, which is U.S. households. There's no mention of the variable. So it would be incorrect to say like lots of U.S. households have pets or lots of U.S. households don't have pets. That would be including the variable. We just want to state the population, which is all U.S. households. All right, and then condition 3. This is the condition that usually changes depending on what type of test you're running. Remember, for a one-sample proportion hypothesis test, we check that same condition very similar to the normal approximation for the binomial. We check that np1 minus p has to come in greater than or equal to 10. So what is the n here? Well, that's our sample size. We know that that is the 240 households. So this is going to be 240 times the p, which remember references the null hypothesis, which is 0.68, and then 1 minus 0.68. So we can type that into our calculator, and that should give us, let's see, 240 times 0.68 times 1 minus 0.68. And after we do that, we should get like approximately 52.2, and of course all we need is to make sure that it's greater than or equal to 10, which it is, so we're all good. So all three conditions for running this one sample proportion hypothesis test have been met. All right, now we can proceed to step 3, which is the test statistic. This is going to be the formula moment. So here it's going to be z. Remember, we're back to having a z-test statistic because unlike the mean procedures, one sample mean, two sample mean, matched pairs, where we had to use t, remember that t-test statistic came from having to estimate the population standard deviation with the sample standard deviation. Here, because we're working with something that is categorical, specifically binomial, we don't have to worry about that approximation of population standard deviation. So we can use our standard z-test statistic. That also means that when we get to step 4, the p-value, we get to use table A rather than table C. So what is the formula then here? Well, remember it's that p hat minus p over the square root of p1 minus p divided by n. So that means we need to know what p hat is, what p is, and what n is. So there are 3 things to know for this formula. So for this p, we've already used that. That's the null hypothesis. So that's 0.68. And the n, that's the sample size. We've already used that. That's the 240. So the only question then is, what is the p hat? Now remember, that notation stands for the sample proportion. So that means we have to actually calculate what percentage or proportion of people in our sample had the trait that we wanted, which in this case was that they owned a pet. Well, that's where we'll actually use this information here. 168 of them owned a pet, so we'll do 168 divided by 240. So 168 divided by 240, and if we do that, 168 divided by 240, we should get that that comes out as 0.7 or 0.70. So in our sample, 70% of the households owned a pet. All right, let's go ahead and plug this stuff in then. So we get 0.70 minus 0.68 divided by the square root of 0.68, 1 minus 0.68 divided by 240. So as usual, let's go ahead and do the top and bottom separately. The top should be easy, it's 0.02. And the bottom, we just type that in as it looks, square root, and then parentheses 0.68 times parentheses 1 minus 0.68 divided by 240. And when we do that, looks like we should get 0.030. And if we then do that division, 0.02 divided by 0.030, looks like we should get a z-score of 0.67. And remember, at the end here, the z-score should be kept to 2 decimal places because that's what we can look up on table A. All right, so there is our z-score. One quick reminder before we move on to step 4 here. Remember that in this denominator here, this is p and 1 minus p. So these reference that null hypothesis. That's why 0.68 is showing up down there. All right, let's go ahead and go onto a new page and look at how we get that p-value. So for step 4, we want to go ahead and get the p-value. Remember that with this, it's probably nice to go ahead and do a quick diagram. So we're going to draw our bell-shaped curve. And our middle, we can label it at the actual value, or if you prefer, you can just label it as the null. Then you can put our point of interest, which is going to be over here because we found a positive z-score. So this was at z equals 0.67. And then which way are we shading here? Well, this is what's based on the alternate hypothesis. We said that the alternate hypothesis was p greater than 0.68, which meant it was a right-tailed test. So our shaded area here is going to be this stuff right in here. So that shaded area is our p-value. So how do we actually find that? Well, we have z is 0.67. So we can go ahead and use table A, and we can look up this z-score. So we're looking up 0.67. So let's go ahead and do that. There's the positive part. So if we go ahead and do that, there's 0.6, and there's the 0.7. So if we just run those together, there we go. We have 0.7486. So there we go. Now let's go ahead and record that. So our table value is 0.7486. So 0.7486. Okay. And of course, that remember, table A always tells us the area to the left, so we can fill this in here as 0.7486. Now, does that match our shaded area? Well, no, that would tell us all this stuff over here, but we actually want the stuff to the right. So remember, we can get our p-value here by doing 1 minus, because the area under the entire curve has to be exactly 1. So our p-value is 1 minus 0.7486, which gives us 0.2514. So there we go. We have an exact p-value. Remember, that is one advantage of these proportion tests, is that you do get an exact value for the p-value rather than a range. And that's just because we have a little bit more information on table A than we have on table C. So there we go. We have our p-value. Now let's go ahead and make a conclusion, which we can do right here. So our conclusion, so we have our p-value equal to 0.2514, and we want to compare that against the alpha that was set in the problem, 0.05. So how does this p-value compare against this alpha? Well, it should be very clear that the p-value is significantly larger than the alpha. So what happens when your p-value is larger than alpha? Well, that means the statistical conclusion is you fail to reject HO. And remember that a failure to reject HO is a failure to find evidence for your claim. So we would say no significant evidence. That, and what was our claim? Well, if we go back and look, we can look in the language of it to study if this percentage has increased, or right here to claim that the percentage of U.S. households that own a pet has increased since 2010. So there's no evidence for that claim. So we'd say no significant evidence that the percentage of U.S. households that own a pet has increased since 2010, or you could say from 68%. So again, either phrasing would be okay. No significant evidence that the percentage of U.S. households that own a pet has increased since 2010, or no significant evidence that the percentage of U.S. households that own a pet has increased from 68%. All right. So to quickly recap here, what really sort of happened behind the scenes here? Well, the big thing is that in our data, in our sample of 240 households, we found that 70% of those households owned a pet. Now, 70% is definitely a bit higher than 68%, but what we're saying is, based on the sample size being only 240 households, that 70% is not big enough or far enough above the 68% to really believe that there's been some fundamental increase in that percentage. Definitely our sample had a higher percentage, but that's not enough to convince us that the overall population has had that increase in the percentage. All right, now we're ready to move on to part B, which is going to be building a 95% confidence interval for this. All right, so let's go ahead and do that. So this will be part B. So we want to do a 95% confidence interval for the percentage of U.S. households with pet. Okay, so for confidence intervals, remember we have two steps. First, we need to start with the conditions. Now, back when we were doing the sort of mean-based procedures, the conditions for the confidence intervals were exactly the same as the hypothesis test. The one sample proportion, however, is a little bit different. We have to be careful here because the third condition is a bit different. So what we can say here is that 1 and 2 are already checked, so we're good there. Okay, but we do need to confirm condition 3. Why is condition 3 for the confidence interval different? Well, remember that condition 3 back here was based on checking NP1 minus P, which meant that it referenced the null hypothesis. But obviously, when we're doing a confidence interval, there isn't a null hypothesis. So it doesn't make sense to use the same condition. Instead, remember that for condition 3, for a one sample proportion confidence interval, we need to confirm that there are at least 10 successes and 10 failures. So let's check the number of successes. How many households said they had a pet? Well, if we go back and check, we know that that was 168 of them. That was our successes. So we have 168, and that is greater than or equal to 10, so we're all good. And then the failures. Well, how do we figure out the failures? Well, remember, this is a binomial categorical variable, so people either owned a pet or did not. So our failures can be found as doing 240 minus 168, the 240 representing the overall sample size minus the 168, the people who were successes. And if we check that 240 minus 168, that should give us 72, which is greater than or equal to 10. So we're all good. So in other words, we're saying that 168 households had pets, 72 did not. 168 plus 72 gives us the 240 overall. All right, now that we've checked that extra condition or that different condition 3, we can go to the construction. The formula for a one sample proportion confidence interval is p hat plus or minus z star square root p hat 1 minus p hat over n. So there are 3 things we need to know here. So we need to know the sample proportion, the sample size, and that z star. So remember, for the sample proportion, we could just use what we already did, or we can just recalculate it. It would be the number of successes, 168, divided by the sample size, 240. And we know that that comes out is 0.7 or 70%. And the n, of course, the sample size, we know that that's 240. And z star, well, remember, we can look this up on table C if we like. We can go to table C. We can look up the z star and go across to the confidence level, which is 95%. But you guys are certainly welcome to go check this on table C if you want. But keep in mind that we said with z stars, you can sort of memorize or just remember the couple major z stars. And for 95%, that z star is always 1.96. So you can go check that on table C if you like, but we do know that this comes out as 1.96. All right, let's go ahead and put this stuff in then. So we have 0.70 plus or minus 1.96 square root 0.70, 1 minus 0.70 divided by 240. as is usual with confidence intervals, we'll go ahead and calculate the margin of error first. So we'll type that into our calculator, 1.96 times square root, parentheses 0.70, times parentheses 1 minus 0.70, divided by 240. For that margin of error, we should get 0.70 plus or minus 0.058. Then let's go ahead and actually build our interval. Let's do our subtraction first, 0.70 minus 0.058. And we should get as the low end 0.642. And then the addition, 0.70 plus 0.058, we should get 0.758. So there we go. Now we can write our interpretation. We're 95% confident that, well, remember what we're estimating. We're estimating the percentage of U.S. households with a pet. We can convert these into percentages. So we can say 95% confident that between 64.2% and 75.8% of U.S. households own a pet. So in other words, we're saying that the percentage, the true percentage of the entire population that own a pet is somewhere between 64.2% and 75.8%. Notice that this confidence interval confirms what we did back in part A. Remember, we failed to reject 68%. We had that 68% coming from a study in 2010, and we said we don't have enough evidence to throw it out. And of course, that makes sense here because what's in this range? Well, 68% is right in this interval, so we had no reason to throw it out. All right, let's wrap this example up with part C. So we want to just talk about the sampling technique. So again, remember for sampling technique, we have the choices of SRS, systematic, stratified, cluster. Of course, we could also be convenience, but then we know that it wouldn't have been valid to go ahead and do these inferential procedures, the hypothesis test and the confidence interval, so we can rule out convenience sampling. So which of these is it? Well, if we go back to the text, we can see that there was this process before we did the study of dividing the country into 4 regions and then sampling 60 households from each region. So what does that tell us? Well, there was a classification, and then we made sure to choose some individuals from each, or some households from each region. That makes this a stratified sample. So this was stratified, and of course, if you want to make a note, the strata were the 4 major regions. So there we go. So all of this first question was about running the one sample proportion procedures. First the one sample proportion hypothesis test, and then the one sample proportion confidence interval. All right, let's go ahead and take a look at question 2. So for question 2, we're saying that we're interested in studying if younger adults, 21 to 25 years old, and older adults, 50 to 55, in the U.S. have different opinions on the importance of seatbelts. So to study this, you randomly sample 300 younger adults and 200 older adults from the U.S. and ask them, considering that a seatbelt could save your life in the event of an accident, do you always wear a seatbelt while driving? So we find that 275 of the younger adults answer yes to the question, while 190 of the older adults answer yes. So let's go ahead and see what we need to do here. In part A, we're going to carry out a hypothesis test at alpha equals 0.05 to test the claim that the percentage, as soon as we see that in there, we know that we're talking about one of these proportion procedures. Notice that we're testing the claim that the percentage of younger adults who always wear a seatbelt is different than the percentage of older adults who always wear their seatbelt. Well, notice that we're doing a percentage from one population, younger adults, versus a second population, older adults. And that tells us right away that this is going to be a 2-sample proportion procedure. We'll, of course, check all the conditions and state our conclusion in the context. Then in part B, we're going to do a little bit of error analysis. And then in part C, we're going to go ahead and do a little bit of review again and talk about potential sources of bias in this study. So let's go ahead and start with part A. So we've already determined that it's a 2-sample proportion hypothesis test. So we have 2 samples of binomial data. Right, so we have 2 samples of binomial data. One of the samples is from younger adults, one is from older adults. How do we know that it's binomial? Well, because when we ask this question about whether or not you always wear a seatbelt, there's only 2 answers, yes or no. So it's a binomial categorical variable. All right, let's go ahead and start with part 1, which are the hypotheses. So we have our null and our alternate. So remember, just like with a two-sample mean procedure, the null hypothesis for a two-sample proportion is always the same. There's no sort of work we have to do here. It's always just going to be that P1 equals P2. Now, in this case, we can use some subscripts. We can maybe say P sub Y sub A equals P O sub A. So I'm using Y sub A for younger adults, O sub A for older adults. What is the alternate? Well, now we look for the claim. Notice that the claim here is that the percentage of younger adults who always wear their seatbelt is different. What does different indicate? That means not equal to. So our alternate is going to be Py sub A not equal to Po sub A. What does that tell us then? That makes this a two-tailed test, or two-sided if you prefer. Either language is fine there. Okay, so there we go. We have our hypotheses. Notice a little bit easier here because we don't have to find a value for the null hypothesis. All we had to do is realize that different indicated we were using a not equals to, which told us it's a two-tailed test. All right, let's go ahead and look at the conditions. So remember that whenever we're doing a two-sample procedure, the conditions are all going to be that both samples have to satisfy them. So first we need both to be random and representative. So if we go back up here, it looks like we do randomly sample 300 younger adults and 200 older adults. So both random and representative, so that's stated. So we're all good there. Then we need both sample sizes less than 5% of the population size. Again, we automatically know the sample sizes. So we know that there's 300 younger adults and 200 older adults. No mention of the total number of younger adults or the total number of older adults in the US, but we know that there's lots of those. So we just say that. So we'll say lots of younger adults, check, and lots of older adults, check. Only thing that we have to be careful here is that, well, we got to say it twice because there's two samples from two separate populations. Finally, for condition 3, remember that condition 3 for the two-sample proportion is pretty different than what condition 3 for the one-sample proportion looks like. Since there's no value for the null hypothesis, we're not doing that NP1 minus P has to be greater than 10. Instead, we're checking that the number of successes and failures has to be more than or equal to 5 in each sample. So let's check successes for group 1. What is group 1? Well, by the way that we set this up, it's younger adults. So how many younger adults said that they always wear their seatbelt? Well, that would be 275. So that's 275, and that is certainly greater than 5. Check. What about failures for the first group? Well, that we can determine by simply taking the number of younger adults, 300, and subtracting 275. So 300 minus 275 tells us that 25 did not always wear their seatbelt, so that's greater than 5, so we're all good. Then for group 2, this is going to be the older adults. How many successes? Well, if we look back up here, it'd be 190, and that, of course, is greater than or equal to 5, so we're all good there. And how many did not? Well, the failures there. So we know our sample size was 200 overall, so we can just take 200 minus the 190 and find out that there were 10 that did not there. So 10 greater than or equal to 5. So we're all good. So there were at least 5 successes and 5 failures for the younger adults, and there were at least 5 successes and 5 failures for the older adults. So all the conditions are met here. So let's go ahead then and move to our test statistic. So once again, this will be Z, and our formula here is going to be P1 hat minus P2 hat divided by the square root, and then we get that P tilde, 1 minus P tilde, 1 over N1 plus 1 over N2. So pretty messy here. A lot of things we need to know. We need to know P1 hat. We need to know P2 hat. We need to know N1. We need to know N2. And we need to know P tilde. So let's remember how we can get all of these. So a couple of them we've already talked about, N1 and N2. We know the sample size for the first group, which is the younger adults, was 300. And the sample size for the older adults was 200. How do we get P1 hat, the first sample proportion? Well, that would be the number of successes, 275, divided by the corresponding sample size. So 275 divided by 300. If we go ahead and do that, looks like that should come in as approximately 0.917. Notice again, whenever we're working with these proportions, I try to keep 3 decimal places because the numbers are, since they're proportions, inherently small. Okay, and then for P2 hat, well, that's going to be the number of successes for the older adults, 190 divided by that 200. So 190 divided by 200. And if we do that, 190 divided by 200, that should come in as 0.95. So, in other words, we've just found that in our sample, 91.7% of the younger adults said that they always wear a seatbelt, whereas 95% of the older adults say they always wear a seatbelt. And then we finally have this pooled sample proportion, that P tilde. Remember that the pooled sample proportion is found by combining the successes and then dividing by the combined sample size. So this will be 275 plus 190 divided by 300 plus 200. So if we do that, that will give us, we can put that here, not quite enough space. So let's go ahead, we'll just scoot this thing over a little bit. So that's P tilde here. That's going to be the 275 plus the 190 over 300 plus 200. If we do that, 275 plus 190 should be 465 up top. And then 300 plus 200, of course, we get 500. And 465 divided by 500, you should get 0.93. So this is our pooled sample proportion. In other words, this is telling us that 93% of people that we sampled said they always wear their seatbelt. Now, notice at that 0.93, remember that always has to land between the other two sample proportions, which it does. And notice that it is slightly closer to 0.917 than it is to 0.95. And that, of course, is because the younger adults wear a slightly larger sample. So this will always be located between the two sample proportions, but it'll be a little closer to whichever sample was a bit larger. Okay, we can now go ahead and plug all this stuff in. So we have that Z is 0.917 minus 0.95 divided by the square root, 0.93, 1 minus 0.93, 1 over 300 plus 1 over 200. As is usual, we'll do the top and bottom sort of separately. So up top, 0.917 minus 0.95, we should get minus 0.033. And then in the denominator, square root, 0.93 times parentheses 1 minus 0.93 times parentheses 1 divided by 300 plus 1 divided by 200. Close up the parenthesis. Down the bottom, we should get 0.023. There we go. And now we can go ahead and do our division. So negative 0.033 divided by 0.023. And we should get negative 1.43 as our z-score. So there we go. We've gotten our test statistic. All right, let's go on to the next page and actually get the p-value here. So for step 4 here, we have our p-value. So we can go ahead and draw our diagram. So there's our bell-shaped curve. There's our null in the middle. Our z-score was negative 1.43. So let's go ahead and put that. Remember, being negative, it's going to be over here. So z equals negative 1.43. Now, what do we want to shade in? What does our p-value look like visually? Well, we go back to our claim. Remember, our claim was not equal to, which meant it was a two-tailed test. So over here, we need to include the mirror image of this over at positive 1.43. So there's z equals 1.43. And our p-value is going to be all of this stuff here and all of this stuff here. Now remember, the area here and the area here are the same. So if we find one of them, we can double it, and that'll be our actual p-value. Always easier to use the negative one, because remember, what we look up on table A is always going to be to the left. So if we look up this stuff, that'll match, and then we can simply double it. So let's take our z equals negative 1.43 and use table A here. So let's go ahead and do that. So we're looking up negative 1.43. And we'll get a good color here. Negative 1.43. Looks like we're right there and there. So we put those together. And looks like we should find 0.0764. So let's go ahead and record that, 0.0764, and we can draw that on. That is going to be to the left there, so 0.0764. Okay, now is this our p-value? Well, not quite, because this would only tell us this area. We need to double it to get our overall p-value. So our p-value here is 2 times 0.0764, which if we multiply that out, 2 times 0.0764 should give us a p-value of 0.1528. So let's go ahead then and make our conclusion. So we can take our p-value, which was 0.1528, and we can compare that against the alpha, 0.05. How does this compare? Well, certainly is larger again. So that means we're going to fail to reject HO. So there's no significant evidence for our claim. What was our claim? Well, the claim back here was that the two proportions were not equal, or if you prefer in the phrasing here, the claim was that the percentage of younger adults who always wear their seatbelt is different than the percentage of older adults who always wear their seatbelt. So there's no evidence for that claim. So no significant evidence that the percentage of younger adults who always wear their seatbelt is different from the percentage of older adults who always wear their seatbelt. So, in other words, there's no evidence that these percentages are different. Going back to what actually happened here, we can see that in our samples, we got about 91.7 versus 95%, but we're saying that while those are a bit different, they're not different enough to think that there's some fundamental, significant difference in the actual populations. Okay, so we managed to go ahead here and do a two-sample proportion hypothesis test. Let's go ahead and take a look at B then here. So in B, right, this is going to be some error analysis. So B says, maybe we can just bring this guy over so we can take a look. Okay. Okay, we'll just bring that over. Let's go ahead. We won't need that because it's going to be included. Okay. Okay. So B gives us an error, and then we have to determine if it's type 1 or type 2. So let's go ahead and read what this says. It said, would falsely claiming that there was no difference in the percentage of younger adults who always wear their seatbelts compared to older adults, when there really was a difference, be a type 1 or type 2 error. So how do we determine if it's a type 1 or type 2 error? Well, let's look at what our sort of false claim or our mistake is. So if we said that we're claiming that there's no difference, right? So we're saying there's no difference. What conclusion must we have made? Well, this right here, claiming there was no difference, this would happen only if we failed to reject HO. Remember, rejecting HO would be saying that there is a difference. So saying that there's no difference is failing to reject HO. So what type of error occurs when you fail to reject HO incorrectly? Well, this would imply that this type of error would be a type 2 error, which is you fail to reject HO, but HO is false, right? This is sometimes what we call a missed effect, right? Sometimes you might hear it as like a false negative. What this is basically saying is that you think nothing has happened, but something really did happen. So in this case, we think that there was no difference between younger and older adults when there really was a difference. So this would be a type 2 error here. All right, finally, let's talk about part C. So potential bias. So we learned a bunch of different types of bias back when we first introduced statistical bias at the beginning of our class. Remember, we had things like sampling bias, which included undercoverage and voluntary response bias. We had response bias, which included general response bias, wording bias, interviewer bias, ordering bias, and we also had non-response bias. So in this situation, let's think about what could have happened here. Well, if we read through this, the first thing that should jump out to us is how we phrase this question. This considering that a seatbelt could save your life in the event of an accident. That's unnecessary language there, and it's sort of slanted language because it's basically encouraging people to answer that they always wear a seatbelt because it's telling you how important it is. So that would be a form of wording bias. So one potential bias here is wording bias, right? That whole considering that right? That whole thing in there, right? That should not be included. Instead, our question should just be simply phrased as, do you always wear a seatbelt while driving? The other form of bias we could argue for here is probably that there is sort of a culturally appropriate response that's expected here, right? If we're asking people about seatbelts because it's like a law while driving, and also because people sort of say that, you know, it's responsible to do so, there is sort of an expected yes response. So we could also argue that there is a general response bias, but this being a sort of sensitive question, since wearing seatbelt while driving is the law. Okay. So those would be probably the two major sources of potential bias. You might say, well, maybe there's undercoverage, but we don't know that, right? We don't have enough information to say that a certain group was underrepresented. You might say that there could be like non-response bias or something like that. But again, we don't have enough information from the problem to know if those really occurred. So these are probably the two forms of potential bias we could support based on the information given to us. Well, that wraps up practice number 10.